Imagine you're sitting at one of those fancy chessboard tables, and you want to play chess, but there isn't anyone else around, so you can't actually play the game. You decide to do some mindless tinkering with the chess pieces, by which I mean you start moving around one knight or horse on the chessboard. Now, if you know the rules of chess, you know that knights can only move in an L shape. So you start mindlessly moving the knight on the board, and then you realize you're hitting the same squares over and over. And after a couple tries, you realize you can find a pattern that goes continuously. You get really excited and start Googling to see if you've discovered something new.
Sadly, you haven't. You've discovered something mathematicians call the Knight's Tour. You shrug and decide that chess has been around a long time. Actually, since 500 AD in India, and it makes sense that somebody in history would have already been bored and alone, messing with a chessboard and a knight.
You learn that there's a method to creating Knight's Tours called the Warnsdorf's rule. While doing the Knight's Tour, you always move the knight to the square where the knight will have the next fewest moves. And of course, you can't land on a space you've already been at or go backwards.
Then you learn cool things like how some tours are open and some are closed. The open ones end when you've landed on all the squares, but closed ones can go on an infinite loop. You also learn just how many Knight's Tours there are, approximately 26 trillion closed tours, including reversals, reflections, and rotations.
There are all kinds of ideas in graph theory that relate to the Knight's Tour. In graph theory, Knight's Tours use the Hamiltonian path. Never mind, go back. So the Hamiltonian path is a path that visits every dot or vertex on the graph only once. The Knight's graph is simply the tour, except without, the chessboard. Logically, this maze of lines and dots can only be used for one thing: shapes.
The Platonic solids are also important for graph theory, and every Platonic solid has a Hamilton path. Platonic solids relate to a lot of things, like crystal structures. Ring a bell, anyone? But what about non-Platonic solids? In 1884, P.G. Tate decided that any polyhedral graph with 3 connectors for every vertex, aka a cubic polyhedral graph, was Hamiltonian. Tate's conjecture stood tall for 60 years before it was disproven by W.T. Toote in the 1940s. This amazing thing known today as the Toote graph was his solution. I shouldn't have to explain the use of polyhedrons, because shapes literally make up our 3D world. So yeah, moving on.
Now back to the chessboard. You try to imagine less abstract uses for understanding pathways. A graph is an abstract idea that can be applied to a lot of surfaces: a random shape, a chessboard, a country, and so on. In that case, there's even more to these wonky paths than meets the infinitely tiered chessboard eye. In 1736, Leonhard Euler solved a problem that had been bothering the Prussians in Königsberg for a long time, a problem known as the 7 Bridges of Königsberg. The city of Königsberg was made up of 2 islands that are connected to the mainland by 7 bridges. The problem is to figure out how to make the path cross each bridge exactly once and end up where you started. Euler's solution? There was no way to do it. No matter where you start from, you can't pass through all the bridges and end up where you started without going through one at least twice.
Euler really liked his Uranian paths, in which a graph visits every edge once. Remember, Hamiltonian paths visit every vertex once. Uranian paths also need all the vertices to have an equal number of degrees to work. We've discussed degrees before.
Both Eulerian and Hamiltonian paths and circuits are used in all kinds of ways in graph theory. While we have already looked at objectively cool-looking graphs and the issue of getting around a city with bridges efficiently, there are other applications and interesting features of both these types of graphs. For instance, mail services need to create the most efficient path for their mail carriers to deliver mail. These circuits can also be used in fragmentary DNA assembly, which helps bioinformatics understand the nuances of DNA better.
Graph theory is a far cry from when you mindlessly decide to fool around with a horse on a chessboard. But it's a small world, and there isn't much difference between a chess piece, a brilliant mathematician, and the very structure of our DNA.